Hi, I'm Stuart Marks. I work on the JDK Core Libraries team at Oracle. In this screencast, I'll be introducing Lambda Expressions, one of the biggest new features in Java 8. What is a lambda? At its heart, a lambda is just a function. A function is a computation that takes parameters and returns a value. Up until Java 8, functions could only be implemented using methods. In Java 8, a lambda expression enables functions to be passed around or stored like data. This last point is a key difference between methods and lambdas. Being able to pass functions as arguments or to return them as function return values is a big deal and enables a new class of APIs and programming styles. Let's start off with a simple example of sorting a list of objects. We have a very simple person class that has name and age fields. It also has two getter methods, getName and getAge. We have a list of person that we've created somehow and populated with data. And what we want to do is call the collections.sort method on this list. We need to pass a parameter to the collections.sort method to tell it how to sort the list. In this case, we want to sort the list by name. What do we have to put where those question marks are in order to tell the sort method how to do this? Conceptually, we want to pass a function to the sort method. We've written a function here called compare that compares two person objects by last name. But we can't pass the compare method directly because prior to Java 8 there was no syntax for passing a function to a method as a parameter, at least not directly. The sort method takes a parameter of type comparator, so we've wrapped our compare function inside a class, comparePersonsByName, that implements the comparator interface. But we still can't pass the comparator class. The reason is that the sort method takes an instance of the comparator interface. And so what we need to do is create an instance of the comparePersonsByName class and pass that to the sort method. This is sometimes a problem because the class that defines comparator is sometimes far away from where it's used. And so if you're looking at this sort call, you might have to hunt around somewhere in your file to figure out how the comparison is actually being done. In order to deal with this problem, we can inline the compare method inside an anonymous inner class. This avoids the problem of having to declare the class somewhere else. But there's a lot of clutter here, both in the syntax and the fact that we are creating a class and creating an instance of it just to pass a function to the sort method. Let's erase the clutter from the code here. What we're left with is the essence of the function that we want to pass to the collections.sort method. It takes two parameters, P1 and P2, both of type person, and there's an expression here that calls a couple methods on them and returns the result of comparing the names of each person. We can rewrite this into our first lambda expression. It's just a function. You can see the two parameters here and the expression that's evaluated to compare them. The parameters are on the left inside of parentheses, and they're separated from the body of the lambda expression by this new arrow syntax. We can reduce the clutter further. Since we are sorting a list of person, the comparator function must be a comparison of two persons. The compiler knows this, and so it uses type inference to determine the types of the parameters. We've left off the type declarations, making the lambda expression even more concise. Note that Java is still statically typed. The types of P1 and P2 are still person. They are determined at compile time. If the compiler doesn't have enough information to infer what types they are, it's a compile time error. Now, sort is still calling the compare method, but we haven't declared this lambda to be named compare or anything like that. So how does it know that it's a compare method? Comparator is a special kind of interface called a functional interface. If you write a class that implements an interface, you have to provide implementations of all of the methods declared in that interface. A functional interface is an interface where you only have to implement a single method. In the case of comparator, it's the method called compare. But since there's only a single method that you need to implement, when you provide a lambda expression for it, you don't have to provide the name. The lambda expression implicitly implements that single method inside the functional interface. Now that we've introduced functional interfaces, why are they important? Anywhere a functional interface is taken as an argument, you can write a lambda expression for it. Let's look at other functional interfaces that already existed in Java 7, even though they weren't called functional interfaces back then. A common example is the runnable interface. It defines a single method called run. To create a new thread, you pass an instance of the runnable interface to the thread constructor. The thread in turn would invoke the run method of that runnable. The example in the middle shows a typical usage of creating a runnable using an anonymous inner class. The line at the bottom of the screen shows a lambda expression being passed as a runnable instead of using an anonymous inner class. In many cases, anonymous inner classes can be replaced with lambda expressions. There's something new here, which is that the run method of the runnable interface doesn't take any arguments. To write a lambda expression and pass no arguments, we have to pass the empty set of parentheses on the left side of the arrow. We've added several new APIs in Java 8 that take functional interfaces and which are therefore usable with lambdas. For example, consider the task of printing out each person in a list of persons. We can use a conventional for loop, or we can use a new for each method and pass a lambda expression. The lambda expression is evaluated once for each element in the list. This might not seem very significant. It looks like we've just rearranged the syntax. But this is an example of internal iteration versus external iteration. This example makes the difference between internal and external iteration more clear. Suppose our list is a synchronized list that is being operated upon by multiple threads. The for loop, which embodies external iteration, is implemented using an iterator. The for loop repeatedly calls the hasNext and next methods of the iterator. Since the list is a synchronized list, each method call on the iterator is synchronized. However, another thread can modify the list between these calls. If this occurs, the next method call on the iterator results in a concurrent modification exception. This example shows that the loop is being controlled from outside of the list, hence external iteration. The for each method on list illustrates internal iteration. This is one method call on the list, so it's synchronized for the entire duration of the call. No concurrent modification exception can occur. The iteration of the list happens inside of this single call, hence internal iteration. Here's another example. Let's say we want to remove all persons from the list named Jones. We can find all such persons with a conventional for loop, but we can't do the actual removal. The reason is that we can only remove elements using the remove method of an iterator, but in a for loop, we don't have access to the iterator that the for loop is using. Instead, we need to write out the loop in long form. We have to explicitly get the iterator and advance it ourselves using the hasNext and next methods. We can call the iterator's remove method in the appropriate place when we've found a person that matches the criteria we've set. This is fairly cluttered code. In Java 8, we can call a new method removeIf that removes each element from the list for which the lambda expression returns true. Here's another example of a new method that can be used with lambda. Suppose we want to replace each element in a list of strings with its uppercase equivalent. We can write a similar for loop that iterates using a list iterator. Within the for loop, we call the list iterator's set method in order to replace the string at that location with its uppercase equivalent. At the bottom, you can see that using the new list.replaceAll method, we can replace each element of the list with the result of having called a lambda expression on that element. In this case, we're converting each string to uppercase version of the string, and we're replacing it into the list. So where did for each, remove if, and replace all come from? We've added methods to interfaces. In this case, we've added methods to the iterable, collection, and list interfaces. Prior to Java SE8, adding a method to an interface was considered to be an incompatible change. It was source incompatible because old implementations would get an error saying that they needed to provide an implementation of the newly added interface method. It was considered binary incompatible because if you had an old class that has not been recompiled against the new interface, calling the newly added method would result in an abstract method error. In Java 8, we've added a new feature called default methods. A default method has an implementation inside the interface. So for any class that hasn't provided its own implementation of this method, the default implementation is used instead. Default methods are just like virtual methods in that they can be overridden by subclasses. List.sort is another example of a default method that has been added in Java 8. This is a replacement for the static method collections.sort. This is an example of replacing collections.sort with a call to list.sort. This doesn't look very different, but it's actually very important. Default methods can be overridden by their concrete subclass, so a particular kind of list can do some sorting based on its own internal data structure organization. By contrast, the collections.sort method must use a generic and potentially slow sorting algorithm that works with every kind of list. Let's look again at the lambda we're passing to the sort method. This is highly stylized code. It takes two objects. We get something from the first object, and we get something from the second object, and we call compare2 on those values, and we return the result. Many comparator functions are structured this way. Wouldn't it be nice if we could replicate that structure more easily? We've introduced a new method called comparator.comparing. This is a higher order function, which is a function that consumes or returns other functions. In this case, the comparing function takes a function that gets the right data from a person object. This getter is called on each of the two person objects and calls compare2 on those values. The comparing function doesn't do the comparison itself. Instead, it constructs a comparator function and returns it. This, in turn, is passed to the list.sort method. We've seen a few examples of lambda expressions that are of the form, given an object, call a method on that object and return the result. This form of lambda is so common, we've created a shorthand for it called method references. Using the new : operator, we can mention a method by class name and method name, and it's equivalent to writing a lambda expression that takes an object of that type and calls that method on it. Here we've rewritten our previous examples using method references. The result isn't necessarily shorter, but in some cases it does serve to clarify the code. This last example shows the use of the pre-existing static import feature to make the code more concise. Notice how making the code concise enables the code to read more like what it's doing. In this case, we take a list and sort it by comparing the person by name. Let's move to a more complicated example of two-level sorting. Suppose we want to sort our list of persons by age. A bunch of people will have the same age, so within an age group, they should be sorted by name. This example shows a comparator implemented using an anonymous inner class. First, it compares the person's ages. If they're different, it returns the result. But if the ages are the same, a second comparison is done on the name, and that result is returned. This looks fairly complicated, but if we break it down, we can see that it's like combining two comparators. We call the first one, If the result is unequal, we're done. If the result is equal, we call the second comparator and return its result. We can use higher order functions to take two comparators and combine them into one. This is a higher order function because it takes two comparator functions as arguments and returns another function, which is a comparator that is a combination of the two comparators passed as arguments. Here's what that looks like in code. First, we call comparator.comparing and pass a method reference to getAge. This creates our first comparator. Then we call a new method called thenComparing on that. ThenComparing takes a method reference getName and creates a comparator with it. And then it combines that comparator with the previously created age comparator. Here's what that looks like reformatted. We've combined the getAge and getName comparators, and the result combined comparator is passed to list.sort. Again, we can apply static import to make the code more concise. Notice how well the code reads. First, we take a list, sort it by comparing the person's age, and then by comparing the person's name. Here's the old and new code side by side. Not only does the old code have a lot of inner class boilerplate, it also embeds some logic that isn't very obvious. If you're reading this code for the first time, it can be hard to understand. If you're writing a comparator like this, the logic is easy to get wrong. By contrast, the Lambda-based code makes it easy to create a fairly complicated structure by composition of smaller parts. It's pretty easy to create comparators using the comparing function. It's also pretty easy to combine comparators using the thenComparing method. The resulting code is clear, concise, and is easy to modify. In summary, lambdas are functions. A lambda can often replace an anonymous inner class. Java 8 defines several new functional interfaces and new APIs that use them, enabling them to be used with lambdas. Default methods enable interfaces to evolve compatibly. Method references are useful shorthand lambdas. Higher order functions enable creation of more complex functions via composition of simpler functions. Lambdas make code read more like the problem statement. The resulting code is clear, concise, and easy to maintain and modify.